So to start to understand true color science, we have to go through a really basic question. And I'm going to go through it slowly, but let's start off talking theoretically about red and blue. Now, what do we know about red and blue? Mix red and blue together, you get purple. You've known this since you were a little kid. You know this. It's not a big deal. So the question, however, is this. Is the resulting color purple lighter or darker than the original red and blue? And you have to think about that for a second. You're thinking, I don't know how to answer that. Well, we'll go back to this. The more paint you mix together, does it tend to go lighter or darker? And the answer is, it tends to get darker. When you mix paint together, the resulting spots tend to go darker. This is the way it works. Not 100%, but most of the time that's what happens. You mix red paint and blue paint, you're going to get purple that is darker. Darker is the technical term. Now imagine for a moment we talk into another side of things. I have a flashlight here. It's invisible, right here, flashlight. It's a red spot on the wall. And I've got a flashlight here with a blue spot on the wall. And if I were to shine both flashlights on the same spot on the wall, don't worry about the color, but will it be brighter or darker? You can think about that for a second. Red flashlight, blue flashlight. One light source, more light source. And the answer, of course, is it gets brighter. So when you mix paint, it gets darker. And you mix light, it gets lighter, brighter. This is very important as we move forward, because when we're dealing with digital graphics, we're dealing with the screen, and no matter how you slice it, we're dealing with light. So we're going to move away from pigment theory or paint theory, and we're going to talk right now about light theory. Light theory is physics at its finest. So when we're dealing with light, the primary colors of light are red, green, and blue. These are the primary colors of light. There it is, done. Absolutely. You may hear the term RGB, which while it may stand for red, green, and blue, RGB are letters, not colors. So if somebody goes, what are the primary colors of light? Don't go RGB, say red, green, and blue. Now we go to the questions. What color do we get when we mix red and blue together? Purple. Aha, we already did that one. But what is like purple but brighter? And the answer to that question is magenta. And magenta is like a very vivid, bright-ish purple, right? Some people start thinking pink, but pink has no blue in it. So we have come over here, and this is our red. We come over here, and this is our blue. We come over here, and this is our green. We come over here, and this is our magenta. All right, next. What color do you get when you mix blue and green together? Blue, green, teal, turquoise. I love the fact we have such an amazing vocabulary for all these words, but the word that we are looking for is cyan. I had a professor once call it cayenne. I'm like, that is a pepper. Cyan, if you know what cyan looks like this. And then lastly, what color do you get when you mix red and green together? Now stop for a moment, and I want you to try to visualize this. Not guess. Theater people know this. Some people know I know what it is because I've heard the word cyan, magenta, and the answer is yellow. And you're like, yellow? Yellow. And here's the thing. Try to visualize it. Try to visualize a reddish green. Interestingly enough, you can't. And the reason that you can't visualize a reddish green is because of a neural short circuit, which I'm going to get into a little bit later. So those are the colors that we're working with. And so let me do this a little bit prettier here, right? So I've got red, I've got green, and I've got blue as my primary colors. And then I have cyan, I have magenta, and I have yellow as my secondary colors, which goes to show you that all color is Jewish. If you're laughing at home right now, thank you. If you're not laughing at home right now, somebody is laughing at home right now, which encourages me to keep telling that joke. All right. Now, interestingly enough, where have you heard the terms cyan, magenta, and yellow before? And you're like, I have heard those terms before. And of course, you've heard those terms. Those are the printing colors. Cmyk. K is an old printer's term for key, and the key color in this case is black. Now, I got to tell you a story here. We talk about the price of gasoline. We complain about the price of gasoline. But if you want to know what's evil, inkjet ink is evil. They sell it by the milliliter. The milliliter. That is 1,000th of a liter. So anyway, a couple of years ago, I'm printing a term paper, and it's more than a couple of years ago, and my printer comes up, ding, you are low on black ink. Now that's a sucker's bet. It wants me to change my ink cartridge while I still have 10% of the ink left in it. And I'm like, no, you keep printing. And I demanded to keep printing, and it's printing page after page. And every day, every page that it's printing, I'm feeling smarter and smarter. Because I'll tell you, a good day for me with a printer would be to see it go from white to gray, black to gray to white. Or even better, if I could hear the printer go to the bottom of the cartridge, then I'd know I did right. But when all of a sudden it goes ding, you're out of color ink. Color ink? That's right, because when it ran out of black ink, it mixed equal parts of cyan, magenta, and yellow for triple the cost of my color cartridge. As a matter of fact, you're seeing really cheap printers not even giving you the black cartridge, which there is just for cost-saving measures anyway, and just mixing equal parts of cyan, magenta, and yellow. Because cyan, magenta, and yellow are the primary colors of ink or paint, and red, green, and blue are the secondary colors of ink or paint. And you're like, wait a second. When I was a kid, they told me it was different than that, and they were wrong. So I have this conversation all the time, and I was having this conversation with a buddy of mine who is a professor of painting. And he's like, are you telling me that red isn't a primary? You can't mix red. You can mix red. He's like, you can't mix red. I'm like, you mix yellow and magenta. I'll prove it to you. So he grabs some yellow, magenta, mix it. That's a good red. So why do we work this way? Why? Where does this come from? Well, if we mention a little bit more, there's that mistake right after Newton, that artist treatise. So we refer to this as the pre-scientific primaries or the historic primaries. They sometimes call them the artist primaries. They're a little bit of red, yellow, and blue. It's a grand lie. It's the grand lie. It's wrong. Matter of fact, I was working with a watercolor book once, and it was like, the primary colors of paint are red, yellow, and blue. But for the purposes of this book, please use this tube of magenta for the red and this tube of cyan for the blue. Same difference. So it's important that we learn to do it right, but what really we start realizing is there is only one color wheel, and this is it. This is the color wheel. Learn to love this color wheel. This will make your life ever much better. There you go. Now, you're like, wait a second. You still didn't answer that lady's question. I'm getting there. So I mentioned to you previously that we're working in mixing light together, and from mixing the primaries of light, we can mix all color. I also mentioned to you earlier that pixels don't exist, that only dots exist in the real world, that pixels only exist in the virtual world or inside of the computer. It's not 100% true for what I'm about to tell you. So let me explain how this works. So in our red, green, and blue world, the red, green, and blue world of colors, inside of every pixel, which in this case we really mean dot, are 3 subpixels, which is what they call them, subpixels. And there is a red light bulb, there is a green light bulb, and there is a blue light bulb. And the question is, what color is the light bulb when they're all on? And the answer is white. And what color is the light bulb when they're on, the dot when they're all off? And the answer is black. So there literally are 3 little colors in there from which we mix all the other colors. Well, how do we do that? Well, now we've got to look at these as individual light bulbs. So let's talk about just the one light bulb. Let's talk for a moment just about the red light bulb. Come on, you can do it. There we go. So there's the red light bulb trying to catch up with itself. So imagine that the red light bulb's an on-off switch. What color is the red light bulb when it's on? Well, very easy. It's red. What color is the red light bulb when it's off? And the answer is very easy. It's black. So now we have 2 states, on and off, red and black. That goes back to a few minutes ago. We talked about all those other colors. Now imagine that there's a halfway point on our dimmer switch. Half red, a dim, dull red. Now how many points do we have? 3. Well, what if we keep subdividing? And if we keep subdividing up until we have 256 shades of red, then we can actually mix our colors. So we can have 256 shades of red, 256 shades of green, and 256 shades of blue. Now, computer scientists hate the number one. No, they really don't hate the number one, but it goes back to a really strange question, which is this. How much red is there in black? None. So why would you start it from 1 to 256? And the answer is you don't. So the way it works is, instead of going from 1 to 256, it goes from 0 to 255. And that you're going to see quite frequently, and you need to get used to seeing that inside of programs. Some programs are going to say 1 to 10, and that's because 1 has 1 of something and 10 have 10 of something. But if the lowest level has none of something, starting it at 0 makes more sense. So whenever you see 255, 0 to 255, that really means 256 levels, but 0 of something. We've seen the number 256 before, and as you remember, when we said the number 256, we already said that anytime you saw the number 256, we'd call that 8-bit. But in this case, I love that it equals 8-bit. But in this case, we don't mean 8-bit overall, we mean 8 bits per channel. So we have a red channel, a green channel, and a blue channel. So we have two ways of looking at this. We can either take 256 shades of red times 256 shades of green times 256 shades of blue, and we get 60 million colors, or we can look at it like 2 to the 8th power, right, times 2 to the 8th power to the 8th power, which of course if we add them together, we get 2 to the 24th power, which of course is the same number of colors, which is 16.7 million colors. So the answer to the lady's question, how do you know they're there? It's a mathematical certainty. We are mixing the colors together. RGB, 000 is black, 255, 255, 255 is white. Now we have to start thinking about these other numbers. And this is, by the way, how color is dealt with in our 8 bits per channel, what they call 8-bit RGB. Now 8 bits overall means 256 colors. 8-bit RGB is equal to 16 million colors. So that would be, there you go. That's 8-bit RGB. So that's how this works. So 256 shades of red, green, and blue mixed together. Now, again, some of these you can do. Like, what do you get if you get 255, 255, 0? Well, that's the red light bulb and the green light bulb and none of the blue light bulb. So we know from this one that would be yellow. It's red and green makes yellow. So this is all we're trying to put all this stuff together, which is what makes our life a little bit easier or more complex. Now, that's 8-bit RGB, or 24 bits overall. Dangerous thing right now, marketing perspective. Your scanner will call it 24-bit. Photoshop will call it 8-bit RGB. They are the same thing, and it's going to get used to the verbiage. What if, however, instead of having 8 bits per channel, which we know what's 8-bit, 8-bit is, 2 to the 8th power, right? 2 to the 8th power is that. What if instead of having 8 bits per channel, we had 16 bits per channel? What if instead of going 0 to 255, we went from 0 to 65,535? How many colors would that be? Well, that would be 16-bit RGB, which is also is the same as 2 to the 48th power, which we learned as a lot. Can't even give you a number for it. More importantly, if you find yourself working in 16-bit RGB in Photoshop, most of your features are going to go away. 8-bit is where we live in. You're going to find that you can't save the file in normal file formats. We're going to get to the next video. All these things become difficult for us to play with. So RGB 16 is something we want to avoid. Why does it exist? Well, there's reasons it exists. But more importantly, here's a good question for you. Let us talk for a moment about grayscale, black and white. When we say black and white, it's a euphemism for grayscale, right? We say black and white, we mean from black to white. So black is 0, 0, 0. Great. White is 255, 255, 255. Great. What's 254, 254, 254? Well, it's not white. It's the lightest gray before white. Fine. If 0, 0, 0 is black, what's 1, 1, 1? Well, it's the darkest gray before black. And if you realize that at any given moment, if all three numbers are the same, it's a shade of gray. Right? 127, 127 is neutral gray. 127, 127, 128, 128, 128 is also a gray. So if you're talking about a true neutral gray, we're dealing with where all three colors are the same. So how many shades of pure monochromatic gray are there in those 16.7 million colors? Right there. 256 from white to black. 256 shades. That's it. So if you were a scientist and you needed more than 256 shades of gray, think X-ray for a moment, then you might want to move into the 16-bit RGB or even the 16-bit grayscale mode, because then instead of having 256 shades of gray, you'd have 65,000 shades of gray, which gives you a better and more useful contrast. That's what we're talking about, is the fidelity of contrast. Which brings up this new term that I want to bring up, which is something called gamut. So one of the things that I want to remind you about color itself, and all of this understanding of color will make you a better understanding of editing. Because I want you to remember, if something goes wrong with a photo, you'll go, can you fix that photo? What do they mean? They mean the color. Because if they didn't mean the color, they'd say it. They'd go, can you straighten that photo? Can you make that photo crisper? But if you say, can you just fix it? Usually it's the color. So let's come over here and talk a little bit about color from a biological perspective. Oop, let me put that over here. You don't need to see that just yet. So this horseshoe shape is what color scientists use to describe color. Color is a human biological term. How do you define color? Well, here's the definition of color: that which this can see. If the human eye can see it, it's color. If the human eye can't see it, it's electromagnetic radiation. That's it, period. This is the detector. It is a human biological term. That's what color is. It allows us which part of the frequencies out there can the human eye see. And if you look at this horseshoe shape, which really is three-dimensional, and I'll show you a demo of that in a minute. If we look at this horseshoe shape, what you'll notice is that we can see more greens than anything else. Why? Well, because up until recently, that was the dominant color on the planet. And if you're going to be in a world that's green, if you're going to be running through the jungle or running through the forest, the more shades of green you can differentiate, the better you'll be able to eat. It's all about food. I always joke that there's going to be a version of Jared billions of years in the future. It's like, if you look at the color wheel, we can see more shades of beige than anything else. I hope that's not true from an evolution perspective. Now, if you look over here, you're going to see two other shapes. This yellow triangle is what's referred to as a gamut. And a gamut is a subset of colors that a particular device can represent. And what that means is that this yellow gamut is the gamut for a typical RGB monitor, which is what you're viewing on right now. So technically this whole thing's an illusion. What you realize is that when you look at a computer monitor, computer monitors show a lot of green, but they do not really do yellows or oranges very well. It's just the nature of the primary colors that a computer monitor uses to define the red, green, and blue primaries. That's what happens, is that they're limited by what they do. What's interesting is that if you choose 16-bit or 8-bit, your yellow triangle doesn't get any bigger. It just gets denser. I want you to look at that, right? There's no redder than red. There's no greener than green. There's no bluer than blue. There's no blacker than black. So what happens is you get more subdivisions subtly in the triangle, but nothing more. So this is what's called the Rgb color space. And it's a subset of what we can see, which is why there's no substitution for going to the museum. The reality of it is that we can mix paints and colors and pigments that we still cannot show on a regular computer monitor. Over the years, they've gotten better. And I'll tell the story, and I like to tell the story, but many, many years ago, Dell sold a computer monitor on a laptop that has a larger triangle than a regular laptop. And I pushed for it. I'm like, I need this. Do you know who I am? No, I pushed for it, and I got this laptop, and it was so bright. The screen was so bright, and it was so heavy. And you can't complain about it because I just pushed to get this laptop. So I had this really crazy extended color laptop, and it was great for looking at pictures, but nothing else. Let's talk about this blue polygon for a second. This blue polygon represents another color space. And this time the color space is that of the standard Cmyk printer. As I mentioned, Cmyk, cyan, magenta, yellow, and black are the colors that are mixed together to create the printable colors. And what you'll notice is that while they can print yellows and oranges that the computer monitor can't display, there's a huge range of vibrant greens that are just outside of the range of printing. Standard color printing. Which is why you're going to see that fancier printers have more and more colors in them. I've got a 9-color printer downstairs that allows you to actually have more pins to create what's called a wider gamut to try to print more vibrant greens or more vibrant yellows. And that's why people who do professional printing will go out and go, I need a Pantone 12, and they'll literally grab this one type of paint and mix it in because it can't be made from the primaries or the primaries we're using. Or if you're ever working with things like Day-Glo paint, whereas like you're not going to mix that here, it's going to have to come in from another place. I've got a couple of videos that I want to show real fast to help demonstrate my point. If we were meeting in class, by the way, I actually have a light box, and the light box allows me to take a red, green, and blue spotlight and mix them together like this. And when you see the white coming together, that's pretty exciting. But the red plus green making yellow freaks everybody out. And again, the reason it freaks you out is because you're not used to seeing it in your mind's eye, because you, from a neural perspective, and I'll do this in a second, you can't visualize a reddish green, but you can see yellow. So this is a great little demo there. But I love showing it in class because this is how color works, is you mix the red, the green, and the blue lights together and you get white or yellow or magenta or cyan. Next, cancel. Next, I'll play this little video right now. Saw this video years ago. Could not be done better than this. Except for the additive.
Additive display systems, such as television, simulate color appearance by combining red, green, and blue primaries. Because the human visual system creates the perception of color using 3 types of light receptors, color can be graphically represented in a 3-dimensional space. This RGB cube is the gamut of a contemporary xenon digital projector. Different choices for the RGB primaries define different gamuts. For example, digital television's color gamut lies within that of our digital projector. This is because television's RGB primaries are less saturated. Of course, the human visual system can perceive colors outside the range of both of these devices. These are the pure monochromatic colors of the visible spectrum. As the most saturated colors, this contour defines the limit of human color perception. Extending the spectrum to multiple luminance levels, we observe that the RGB color cube is completely contained within the visible locus. Indeed, all color reproduction gamuts lie within these bounds. Normalizing the spectral intensities and altering our vantage point, the spectral locus takes on the horseshoe shape familiar to color scientists. Rotating back, observe the multitude of colors which are present in the real world, but lie outside of the RGB gamut. In 1931, the CIE defined 3 primaries, X, Y, and Z, which are distinct in that they are not tied to a physical display device, but rather lie outside of the visible gamut. Furthermore, the XYZ primaries completely enclose the visible gamut, by definition encoding all color perceptions possible in the real world. Thus, the XYZ primaries can be used to describe color in a manner independent of any current or future display technology.
And one more, just because it's fun.
At Sharp, our goal is to reproduce every color in the world on TV. Introducing Quattron Quad Pixel technology. It adds a 4th color, yellow, to the standard RGB color system, creating a vast array of colors you can't see with your TV's 3-color technology. But you can can see this. Whoa! Oh my.
Quattron from Sharp. You have to see it to see it.
And I'll be honest with you, those Quattron were the coolest things, because what you could see, they have a little magnifying glass and you could look. Because if you actually look at a magnifying glass, you'll actually see what they call the subpixels. It's kind of weird. Dots are made of subpixels, but they're not really made of pixels. But you can see the little red, green, and blue arrangements of them. But with the Quattron, you would actually see a yellow in them, and it would actually create a wider gamut. It was the coolest display technology. I don't know if they're still selling them or not. They're definitely not hyping them the way they were a few years ago when they came out. George Takei is so great as a salesperson on that. So again, there's this human-centric approach to all of this, which I want to kind of go back to about why we're looking at color the way we do. And so much of what we do is based on the three parts of color, right? There's three parts of it. There's the physics of color, there is the biology of color, and there is the psychology of color. Let's round out our color discussion for a moment. So let's talk about the biology of color. So the biology of color is as follows. So if we look over here, what we're seeing is that our inside of the eye, there are three receptors. There's two types of receptors inside the eye. There are rods and there are cones. The cones see color and the rods are monochromatic. The monochromatic, they see basically shape and grayscale. Rods aside, there are three types of cones: short, medium, and long. The long, we view them as basically long is red, the green is medium, the short is blue. It's not only true is they peak, there's overlap in them. So the reality of it is, if you look at over here, there's overlap between the medium and the long. There's overlap between the short, the medium, and the long. So there's a lot of redundant data here being fed. So while we're only able to see the frequencies, by the way, that the cones allow for, and that's what we're looking at here in terms of frequency response. Now I've got a great little demo for you here. I wish somebody was here for me to volunteer. So if I were to grab something nice and colorful, there it is. If I were to put it out into my peripheral vision and I were to look forward and I were to bring this until I can see it, at some point, if I'm still looking forward, I'll only be able to see that it's there without actually seeing the color, because the cones are only in the center of your eye. Your peripheral vision is monochromatic. It's such a fun thing. Again, if you grab anything, don't grab a black pen. I hate people who say, oh my God, it's black. Of course it's black. Find a nice big colored marker, put it off in your peripheral vision, put it right behind where you can see, stare forward, and bring it forward until you can start seeing the movement. And once you can start seeing the movement, you're going to realize that you can make it out. Again, if you look forward, you can make it out, but you cannot actually see the color. Freaks people out. But don't worry, even though I've just shown you this, it's always been that way. Your peripheral vision is monochromatic. It's always been monochromatic. You just have now realized it, because anytime you see something, you turn. And there's that sense of how we feed together. So again, the physics of it is RGB. The biology of it is spiked at RGB, but where it gets messed up is a neural circuit that happens to try to make the best of all of this data. What do I mean by that? Well, it turns out that inside of your optic nerve, before it hits your brain, in something called the opponent process theory, the three signals, the short, the medium, and the long, come together to create a more compact signal. So what ends up happening is that while you end up having the short, medium, and long cones feeding data, they're actually processed before they hit the brain in the optic nerve into three channels: the blue-yellow channel, the red-green channel, and the black-white channel. Oops, let me move this so you can, there we go. The blue-yellow, the red-green, the black-white. Why this matters is that if I were to ask you to close your eyes and envision a yellowish blue, it hurts. Same with the reddish green, because the way that our data is processed is we see blue or yellow or red or green. The continuum is such that we can't see them both at the same time in the same field because of the way that the data has been processed here. And that's why we're going to be dealing with this is the perceptual side, not the biological side. Sort of a weird thing. The brain gets a different signal than the eye is recording than the world actually sees. That's the fun part about color theory. All right, let's get out of some of these things. Delete. No. Oh, wait. delete. Yes. Sorry, I'm so used to saying no. It's the delete. Yes. Again, that's how we know it's really there. So everything we're going to do in color is going to be basically typing in numbers. 0, 0, 0 is black. 128, 128, 128 is gray. 255, 0, 0 is red. This is how we look at color. Next question. It's a good question. What color is 127, 32, 8? And the answer is, I have no idea. Neither do you. And the reason is I already told you, you are not an RGB being. You actually feed these other colors and you see it in another way. So I want to talk about color in a whole other way. So we've got RGB, there we go. Cmyk we'll get to a little bit later on. That's more about printing, and nothing we're doing right now is in print. And so much what we do, even when it's in print, we still work in RGB mode. But let's go back to our color wheel. Our color wheel. The color wheel. The primary colors are red, green, and blue. The secondary colors are cyan, magenta, and yellow. Unless we're dealing in print, the primary colors are cyan, magenta, and yellow, and the primary colors are red, the secondary colors are red, green, and blue. So right now we're so used to working again in what's called RGB color mode. However, when we talk about color, I'm going to jump the gun because we're going to see it a little bit later. And this does happen. It happens in every program. Photoshop, Illustrator, I don't care what you deal with. This is the way the colors works with. Instead of dealing with the red, green, and blue values, which is, by the way, what the programs will deal with, we can actually do something called HSV. HSV stands for hue, saturation, and value. Sometimes you're going to see HSB, which is brightness. There are technically some mild variations in there, but for our purposes today, each one will work the same. Let's talk about hue. This is a circle. How many degrees in a circle? 360 degrees in a circle. So that means if I were to come over here and subdivide, that's 6. That means that this would be 0, 60, 120, 180, 240, 300, and going back to 360. So 0 to 360. So any given moment, we're talking about the pure rainbow hue, we can look around the circle. So if red is 0 and yellow is 60, what color would 30 be? You're like, orange? You'd be right. Very good. What color would 28 be? You're like, a reddish orange? Exactly. So the idea being is even though you don't know exactly what color it is, if I were to pick any color on the number on the color, again, number on the wheel, you should be able to point to that and find its pure absolute color, its pure hue. Now, we need to modify that number. So the hue is a number between 0 and technically 359, but people will let it spin to 360 and understand that 0 and 360 are the same thing. So 0 to 360, wrap around. Now, when we talk about saturation, we're talking about how much white has been mixed into it. So what we talk about is saturation is how much white, and we tint with white. So if the saturation is 100, there is no white. So pure red. If the saturation is 50, that means we've got 50 red. So we 50 white. If we mix red with white, we get pink. And if we keep mixing in more white, more white, more white, more white, eventually we get white. That's the way it works. So saturation is 100 is no white, pure saturation of color, but we tint with white. And with our brightness, we shade with black. 100 is no black. And of course, 50 would be like a dark red, right? We don't really have a good word for that, dark red. And of course, when we go through together, we pick our color, and then we go through and we tint and we shade it, and we get the right color we're looking for. And the HSV values are very easy to look at, and then they'll translate back to RGB. And we'll play with that in our color picker a little bit later, not right now. But when we do get back to our color picker, this is the moment I want you to remember. So while this is how the computer's picking color, this is an easier way for you to pick color because it makes more sense and it works both ways. Just so you know, we don't mix color. You really don't want to be, you would never give kid a tube of black and white paint. If you wanted somebody to have a gray, your best bet is not to give them black and white and have them mix them together. Your best bet is to actually extinguish with the opposite color. If you look at the color wheel, blue and yellow are opposite each other. If you mix blue and yellow together, you get gray. Red and cyan gets gray. Magenta and green gets gray. And the idea is that how we can move things around the color by putting the opposites together, that becomes a little bit more advanced in our color theory, which we'll get to in a little bit. But now, let us remember, we have pixels, data, dots filled with pixels. Those dots have 3 subpixels, a red, a green, and a blue light bulb. And depending on how we turn those light bulbs on or off, we end up getting different colors, which are laid out on a grid, which we call resolution. Oh my God, it's all coming together. So what do we do now? Well, I have to put it in a box. I have to grab a box, and I have to put it in a box. What am I putting in the box? I'm putting data. Putting data in the box. Well, what kind of data is it? Well, let's take a look for a moment. Let's go back to a theoretical moment that I have a screen that is 1024 by 768. Right? If I do that, that's 786,432 pixels. Now, each of those, it's only 750,000 pieces of information. So you're looking at the screen, and it's 750,000 pieces of information. Hell, I'll be more accurate with you. Let's do this one, 1920 by 1080. That's what this is. That's what the screen is I'm looking at right now. 2 million pieces of information. Now, each pixel on the screen, I could write that down, couldn't I? And if I were to write it down, I could write it down using 3 numbers, the red value, the green value, and the blue value. So all I have to do is multiply that by 3, and I get 6.2 million. All right, everybody, please pull out a piece of paper and number from 1 to 6.2 million. Now, while you're not going to do that, or I hope you're not doing that. If you're doing that, stop. If you're not going to do that, I want you to realize that at least you could do that. That if you were to look at this screen, whatever is on the screen right now, those 2 million dots are made up of 6 million subpixels. Those subpixels have a value from 0 to 255, and you could, with a very long period of time, write down all that information, that data, and save it. And that data is saved in a box called a file format. We'll talk about the file formats in a moment, but just so you know, the file formats use one of 3 types of strategies, which we call compression. Compression is what do we do to optimize the way that we're holding that data. So, there's 3 types of compression that we use. None, lossless, and lossy. And for these, I have all examples. I get paid the big bucks for what I'm about to do today. No compression. Well, no compression is really easy. Archivists love no compression. With no compression, every piece of data has its own spot. If you have 6.2 million pieces of information, you better make room for 6.2 million pieces of information. 1 black pixel on a shelf. 1 white pixel on a shelf. 1 white pixel on a shelf. And that means if the whole screen is white, you're going to say white 2 million times. Again, all the pixels around it are irrelevant. Each pixel is saved. And again, this is what's known as a no compression. Now, no compression is cool because we know if you've got 6 million pieces of information, you know exactly how much room you need. 6 million pieces of information. There's no processing done to it. It is saved uncompressed. No compression. Make sense? That one's the easy one. This next one's a little bit more challenging. Lossless. Which is funny because lossless usually shows up as not spelled properly, but it is today. Good for Microsoft. Good on them. Lossless compression. Lossless compression is a little bit confusing at first, but let me explain it to you with a couple of analogies. Imagine you're going on a trip You have a pile of clothes over here and a suitcase over here. Pile of clothes, suitcase, pile of clothes, suitcase. What do you do with the clothes before you put them in the suitcase? I've been doing this for many, many years, and usually somebody goes, wash them. Only the guys. Come on, assume the clothes are clean. So the answer is fold them. Why? Why do you fold the suit? Why do you fold the clothes before you put them in the suitcase? Well, no wrinkles is one answer, but the reality of it is because you want to take up less space. So the question is the shirt that goes out of the suitcase the same as the shirt that went into the suitcase? Yeah. Unless you're paranoid and think they've replaced all your clothes with exact replicas. But the reality of it is that when you fold a shirt, you are compressing it. You're not altering it, but you're compressing it. And when you unfold the shirt, you're decompressing it. We fold data all the time. Ever zip a file? That's folding data. So the shirt goes in, the shirt comes out. We save space. What did it cost us? It did cost us something, and the answer is time. Lossless compressed images take longer to open because they have to decompress. And if we go to save them, I don't mean save by copy, I mean save as in make a new version, then we're going to compress that. That's going to take time as well. So compressing and decompressing, our computers are fast, we barely notice it. But trust me, if we start working with really, really big files and we start dealing with lossless compression, we're going to notice the time it takes. But with non-compression and lossless compression, the same image goes in is the same image that comes out. With no compression, big file. With lossless compression, smaller file, but unaltered, unchanged, just folded and put away. So far so good? Excellent. Now for this next demonstration, I have this picture. Does anybody know what this is? I love showing this picture. I love showing this picture because people freak out. Well, at least art students do. It's a sweater shaver. Have you ever got fuzzies on your sweater? Ever get fuzzies on your sweater? What fuzzies on your sweater is this: you can shave the fuzzies off your sweater. Now the reality of it is it looks good. It may even look as good as it did. It may even look better. But the reality of it is it's this much thinner. And if you keep shaving your sweater, eventually you'll get a hole. And what lossy compression does is it alters the data. It throws away data in a way, in theory, that you don't notice it. But if you keep adding lossy compression to a file, eventually it will get too noisy and it will die. Lossy compression is used only in photographs. It can't be used in drawings because it's designed to work inside of continuous tone photography. People ask all the time, well, give me a better example of how lossy compression works. Well, I don't have a very good visual one. I'll get to one, but I have a really good version of it acoustically. We've all heard an MP3 before. So you've got the original WAV file and you've got this MP3. And if properly encoded, the MP3 should sound identical to the WAV file. It's what's known psychologically as a metamer. It's when two things are psychologically equivalent in a perceptual system. Well, how does it do that? Well, the reality of it is that when you violin plays its note and then waves go off into the ether, the human ear can't hear everything. The human ear can't hear every bit of vibration or frequency. So the first thing it does is like, human ear can't hear that, throw it away. And then there's like 4 other ways in which things get masked and compressed. But the idea is it does an amazing job. Now, the fun part for me when I talk about this is that when we start talking about waves, is that I'm going to come over here and do a very annoying demo. It's a very annoying demo. Make sure you've got your headphones on and not a speaker for this very annoying demo. So it turns out that your frequencies of your ears change over time. And because I'm in my late 40s and you're not, the video I'm going to play is going to play frequencies that I can't hear, as follows. I have no idea if it's going to record properly, so you'll have to tell me afterwards how annoying this was.
We've all used Wi-Fi.
Know how annoying this is?
Stuff like this.
There's an ad.
As we grow older, we often lose the extreme ends of our hearing spectrum. So, how many of the following sounds can you hear? How old are your ears? Okay, if you can hear 8,000 hertz, you're both alive and not hearing impaired. But let's keep raising the frequency. How high could you hear? If you could hear all of those frequencies, you're probably under 20 years old, but that won't last forever. Unlike other organs such as the liver or skin, the inner ear does not have the capacity to regenerate. In your ear, there are thousands of tiny nerve cells called hair cells. These are responsible for picking up different frequencies and sending the signal to the brain where it's processed. But as you age, the continual exposure to noise and loud sounds can break, bend, and destroy these cells. So why do the high frequencies go first? It turns out that the hairs tuned to high pitches are the first to encounter sound waves. As a result, they experience more stress and tend to degenerate earlier, which is why the older you are, the harder it is to hear high pitches.
Ta-da! So, I actually think it did record, because on my other screen I can see a little wave monitor, and even though I couldn't hear anything, I'm literally watching my desktop recording going, there is signal here, there is signal here. It's the funniest thing that they can hear it. It's called a mosquito tone, and mosquito tones are really funny because, again, sometimes youngins like yourself will set your ringtone to it. So in class, you'll know you got an alert, but I won't. There's a bunch of reasons for it, but the idea is that you can take advantage of biological masking to do this. What's even neater is that while we have no computer monitor to reproduce every frequency that the human eye can see, we can, with speakers, reproduce every frequency the human ear can hear. We've cracked audio. We have not cracked images yet. So we've got this thing called lossy compression. Generally, you're going to hear this is called JPEG compression, and people use this as a verb. They don't just use JPEG as a noun, like that's a JPEG file. They go, did you JPEG that? As in, did you apply lossy compression? Now, I've got a couple of examples of where lossy compression fails. So right now here, I've got the Batman logo. Here it is. Ooh, look at that, Batman. Oh, come on. Let me pick it up and move it. There we go. Apparently I'm making it smile. There we go. There's the Batman logo. And if we look at the Batman logo and I would say, how many colors are here? You would rightly go 3. Well, 2 if you're smart. But there's black, and there's yellow, and there's white. That's the 3 colors of the logo. And this logo can be compressed using no compression, or it can be compressed very well using lossy compression, because it's very easy to go white, 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 white. There's a bunch of white, then, that kind of thing. But let me bring in a version of this logo that has been abused, that instead of using lossy compression, it's using lossless compression, it's using lossy compression. And this is what lossy compression looks like. See, what ends up happening is that lossy compression looks at the image the way the human eye is going to look at the image, and it basically alters the data and adds these swirls and dots and patterns that literally, perceptually, you won't see, especially in those high-resolution images, which is why it's great you have a 20-megapixel camera, because a 20-megapixel image can get away with a lot more compression than a 2-megapixel image can. But because this wasn't designed to be JPEG'd, what you're going to see is that at the areas of ultra-high contrast, the edges, it starts doing weird things, which it shouldn't do. It starts generating new colors, introducing new colors, and those dots and swirls, which have been invisible in a photograph, become artifacts, JPEG lossy compression artifacts inside of an image like this. So we have to be very, very careful that we don't apply lossy compression except on images. Now you're like, wait a second, if it's so bad, why would I ever do it? Well, the answer is, first of all, every digital camera that you own already does it. When you grab your camera, when you grab your phone and take a photo, it saves a JPEG. And it's already got compression in there. Almost every image that you get already has some compression. And it's okay. Some compression is fine. And it's usually very, very minimal compression. Now, for our project, we're playing with these TIFF files, and those TIFF files are beautiful. They're uncompressed. And we're going to talk about file formats in a second. But the idea is that whenever you're playing with, you can't be afraid of compression, but you need to realize that it's there. You got to ask yourself what you're applying and what you're doing with it, and then go on from there. Now, one more section before I'll take a break and move on to my next video, and that is the part we call file formats. Oh, file formats. What a disaster. There's an old quote, wonderful things about standards is that there are so many. So there are so many digital file formats out there. Normally I play the file format game where I have them list them all for you. I'll just start listing the common ones. JPEG, PNG, TIFF, GIF, AI, EPS, PGA, PCX, I'm just going through my mind. I'm just listing file formats. And you could go ahead and jump on in. Yell one out if you have one. Now, it's kind of fun when I do this because it is a little confusing at first. So let's come over here and talk about the various file formats that we have. So first, I'm dealing with digital image file formats. In digital image file formats, I'm going to be dealing with here, which means I need to cross out things like AI. AI is Adobe Illustrator. And Adobe Illustrator, I'm going to use a thinner brush for that because I don't like that. Let's make a little thin red pen. There we go. Adobe Illustrator is a vector-based program, and we're dealing with bitmap-based images right now. Matter of fact, another program that I would cross out would be SVG, which stands for Scalable Vector Graphics. While AI is a proprietary Adobe file format, SVG has really come into play to be the vector-based file format that everybody uses. It's called Scalable Vector Graphics. And again, if you're working with a lot of things like laser cutters or any sort of computer-controlled cutters, they're probably going to start with SVG files as a starting point. Interestingly enough, one that comes up frequently that I have to describe to people is the EPS file, which stands for Encapsulated PostScript. People call me up and they go, I have an EPS file, how do I open it? And I go, what's it a logo of? They go, how did you know? How did you know? So graphic designers work in vector-based programs. Graphic designers, when they design your logo, they're going to design it in a way that scales infinitely, because why not? They're smart enough not to give you an AI or an SVG file because they know you don't know what to do with it. An EPS file is a vector-based file format that's designed as a crossover. If I were to come over to Photoshop and open an EPS file, the first thing it says is, wow, this is vector-based. How many pixels would you like? And don't just press enter. Answer the question. It'll actually ask you how many pixels you want. So you've got to take the moment and answer it, because what it'll do is it'll open the EPS as a bitmap, and then you can work with the bitmap accordingly. They do that to be nice, though you don't feel that way along the way. So a EPS is not, and let's come over here and correct myself. We are going with digital image bitmap / raster file formats. Like, wait a second, what a bitmap isn't that a file format? That's correct. BMP is a file format, so is PICT. They used to joke that bitmap was a native file format for Windows, PICT was a native file format for Mac. They are file formats that nobody's really using anymore. By the way, I can show you later, there are going to be 1,000 file formats out there. I can keep listing them. All right, let's talk about the next one. DOCX, right? What's a DOCX file? It's a Word document. Have you ever seen a picture in a Word document? Yes, you have. But just because you put an image in a shoebox does not make it an album. I want you to remember that lots of file formats contain images. That does not make them an image file format. That being said, I should actually put a line through PDF, because PDF is just Adobe's portable document format, is really a container that can hold anything. You can put video in a PDF. Apple calls it a digital image format. You're going to find a lot of people who will call a PDF a digital image format, but really it's a container that can hold anything. Let's talk a little bit about the web. Let's go away from little crazies for a moment and talk about the web. Which of these are web safe? You can put a JPEG on the web, you can put a GIF on the web, and you can put a PNG on the web. And that means the web browser should be able to open them without any other tool. That's what web safe means. I've mentioned a couple of these already. Let's talk about another way of looking at them. Let us talk about compression. Which of these is uncompressed? Now, I want you to be very careful here. The TIFF file can be uncompressed. TIFF files can have none or lossless or lossy. They can have all three. But most of the time, when people think of a TIFF, They think of none. Very important. I was working with a company, I don't want to say the name of the company, and I went over there and I found out they were saving all of their TIFF files using lossy compression. I said, why did you save those TIFF files? They go, we want them to be good. I go, why do you use lossy compression? They go, we needed the space. The TIFF file isn't what makes it good. The lossless, the no compression is what makes it good. So when people say when people say a TIFF file, they mean a TIFF file with no compression. But just so you know, you can really mess up a TIFF file. The next one, of course, that we have is lossless compression. For lossless compression, we're going to use the GIF file. Now, GIF stands for graphics interlace format. And people are going to go, if it's graphics, then shouldn't it be GIF? Well, I'm a little old school, and I will be honest with you. The author of the format calls it GIF. Now, author intention is irrelevant, and if you go to the dictionary, it is pronounced either GIF or GIF. Now, I know people will tell me that I'm being silly about my hard G, soft G thing, and I'm old school. I'm gonna call it a GIF, and you're gonna call it a GIF, and then we're gonna joke about giraffes and all sorts of things. But I want to remind you that if it's an acronym, it doesn't always inherit the flavor of the letters that you're dealing with. For instance, acronyms go, SCUBA is an acronym, and the U in UBA is underwater. So you don't call it scuba diving because the U stands for underwater. You call it scuba diving because that's what they've come up with. You can debate me later. This will not count against your grade. Now, the reason that GIF was interesting is that GIF uses lossless compression. It folds pictures great. The problem with GIF is it is a limited color palette. It's limited to 256 or fewer colors. And that became like a real problem. GIFs had a resurgence recently, which we'll get to in a second. It's nothing to do with the standard digital images. In response to GIF's color problem and a patent issue that was long since gone, they invented something called PNG, or Portable Network Graphics. Both of them are lossless. Interestingly enough, you can make PNGs with no compression, which screws everybody up because they think that PNGs with no compression are going to hurt, but they don't. So PNGs by definition use lossless compression, TIFFs by definition use no compression, GIFs use lossless compression, but they're limited in color. So why the resurgence of GIF? Well, GIF was an amazing standard when it came out, and there were different flavors of GIF, and one of the flavors of GIF was called GIF 89, which was known as the animated GIF. And because it was built into all the browsers that they could play animated little frogs jumping or things twirling, people didn't expect them to go through and realize that you could take film clips, reduce the color sets, and create mini movies and embed them into a single image that the browser is already compatible with. So GIFs become huge because of the animated GIF subset of the format, which is still, by the way, limited to 256 or fewer colors, which is why they always look a little bit weird. Next, JPEG. JPEG, by the way, uses lossy compression. Lossy compression. Yay, lossy compression. Make that one green. JPEG uses lossy compression. And again, it's come to be both a noun and a verb. Did you JPEG that file? Did you apply lossy compression to it? Now, there's some other vocabulary that we need to know when we're talking about lossy compression. Compression levels are usually invisible, but some programs deal with them differently. For instance, when I'm saving an image, they will call it compression. Sometimes they will say 0 to 100, with 0 being no compression and 100 being the most compression, which means bad. Sometimes they will call quality 0 to 100, with 0 being the worst quality and 100 being the best quality. See how different verbiages are going to change things. Adobe, when working in JPEG compression, used to go 0 through 10, with 10 being the best and 0 being the worst. And then what happened is that a few versions of Photoshop ago, someone was like, wait a second, Adobe, your quality 10 isn't as good as their quality 100. And in a Spinal Tapping oops moment, they made theirs go up to 12. So Adobe quality 12 is the same as everybody else's quality 100. And that's because it used to be 10 and they had to change the numbers. That's why you're going to see that weird number 12 there. A JPEG saved with a compression quality of 12 is virtually lossless, is perceptually lossless, and that Batman logo would look great if it was saved as a JPEG quality 12. It would look perfect, however, if it was saved as a PNG or a GIF. Remember, while the GIF is limited to 256 or fewer colors, there are many images that look good in 256 or fewer colors. Logos, charts, graphics, things like that. Obviously, if you need photographs saved saved with a lossless compression, you would then save them with PNG. Well, what about these other ones, TGA and PCX? So there's a million file formats out there, and there's always some industry that's gonna use it. When I was in Turkey, I found out the PCX file format is still used in Turkish carpet textiling manufacturing. Matter of fact, the PCX format was used heavily by anything involving like yarn. So you're going to see things like needlepoint, and anything involved like that industry is going to still maybe use the PCX file format, which is why programs like Photoshop still can save PCX files. Two more to talk about. One, and then I'll take a break. The first one I'm going to talk about is the PSD. PSD stands for Photoshop Document. The Photoshop document opens in Photoshop. It opens in a few other programs, but really it's not a delivery mechanism. You're not going to go, hey everybody, please print my Photoshop document. No, you're going to say, here's my JPEG, here's my PNG. Photoshop documents are project files. They're digital, they're standard, but they're a project file. I'd like you to view them as that. You're going to work in a Photoshop document, but you're going to export one of these other more portable file formats, like a GIF or a TIFF or a PNG or a JPEG. Camera Raw. Camera Raw isn't really a digital image file format. It's actually the sensor data off of the camera. I'll explain how a digital camera works in the next video, and that will make a little more sense. But one last thing before I go. Both PNG and GIF have something that JPEG does not, and that is what's known as an alpha channel. And I do want to go real fast and explain what an alpha channel is and why it's important to you. So for instance, let's come back over here and let me bring in that image of the this thing over here. The sweater shaver. Dun, dun, dun. So if I were to take my sweater shaver over here and I were to put it over here, what you're going to notice is that the white in the sweater shaver is opaque. Do you see that? That really I've got this sweater shaver and this white field. And when I do that, it's actually overlapping things and it's not making things good. And that's because this was saved as a JPEG. But if this was saved as a PNG or a GIF, I could have actually erased that white and left it as transparent. And that transparent thing that you would have would actually allow me that this will be able to come up all the way over here, and this, instead of being white, would be transparent. Transparent is the alpha channel. Now, does it matter when I print? No. But on the screen, when I'm trying to overlap things, absolutely, these alpha channels are very useful. It's an area of transparency. And again, a GIF will hold it, and a PNG will hold it, but a JPEG is always an opaque image. So that's the other difference there. And when we come back, I will teach you everything you need to know about digital cameras.